Alright, in the last lecture, we just did a quick overview of what mass and inertia was. That's an interesting symbol. And we realized that, hopefully we realized, I realized at least, that if you want to find the mass of something, or you want to measure the inertia of something, you have to actually do something to the object. So you can apply a force to it, and you can look at that through the lens of applying the force and seeing what the acceleration is, or you can look at it in terms of work, where you're applying a force over a distance and looking at what the resultant velocity is. And in both cases, you'll figure out what the mass is from those things. And we do much the same thing, really, with moment of inertia. So let's do a case where we have a door. And this will be the hinge for the door. And the door itself will be like this. Okay? And let's just, for the sake of this problem, assume that we have a length of 1 meter for now, and that the width of the door, so this part, the thickness, is pretty small. It's negligible compared to the length, even though my drawing doesn't necessarily indicate that. And the other bit that we'll put in here is, let's say that we apply a force of, well, some force F for now. We might vary this as time goes by. And I'm going to make sure that, for now at least, I'm applying it perpendicular to the radius. So this would be the radius here, or the lever arm would be in this direction, and that happens to be, because I'm applying it at the edge of the door, the radius, or the lever arm, would be equal to L. So these are my basic parameters for the door. And what's going to happen, though, is we're going to take this door and we're going to rotate it. So here's the door, and it's got its pivot point here, and at some point later it's going to be rotated through some angle theta. And I'll say that this takes 1 second, and that theta here is equal to half of a radian. This is a fair amount. This is fairly representative of half a radian. You can imagine you go through 6 radians in the full thing, so half of a radian would be, 1/12 of the way through. And so it's about this angle. Now, one thing that we can do is, what we're really trying to get at here is, what is the property that governs how hard it is for us to twist this door? And actually, I did this the wrong way. This doesn't make any sense. Let me quickly correct this. And we'll have a force going this way. Okay? So the force is going this way, and it's going to cause the door to twist. And my question is, what is the property of the body, or how can we determine the property of the body that resists the changes in the motion? Because if we're pushing on this and we're causing it to change its motion, because it was just sitting here, okay, so I can say the initial motion of the door was nothing, and then obviously it moved. How did we cause that to happen, and why was it hard? What would make it harder? What would make it easier to twist it? So that's what we're going to look at. And to do that, first of all, I feel like we're going to need to address a little bit of other stuff called angular kinematics. Because right now I've given you some givens. Right? I've given you that the initial position was 0, the final position of the door was half of a radian, the initial angular velocity is 0, the final angular velocity, not quite sure. Alpha, the angular acceleration, we don't know either. And the time I gave was 2 seconds. Now, one of the things that we know is that ultimately we're going to need to get, if we want to find out something involving the change in the motion, just like we did with force up here, we had a force over an acceleration. So it's a reasonable guess that we're going to need to figure out what is going on with this angular acceleration. I could just give these numbers to you, but I want to make sure that I give you an example of how to solve an angular kinematics problem. So what I have here then is everything except for alpha and the final angular velocity. So I don't care about that. That means that I set up the no final angular velocity equation. And the nice thing about this, with the numbers that I gave you, is that this is 0 and this is 0. be sure that we're crossing out both of these, right? Because if I have 0 times t, I don't get t, I get 0 for the whole quantity. That's why I'm crossing that out. And so then if I just do a little bit of rearranging, after I do this, I'll end up with 2 theta over t squared equals alpha. And so for this particular example problem, where theta was equal to 1/2, I have 2 times 1/2 divided by 1 squared. That's 1. So this is accelerating at 1 radian per second squared. That means that every second, the angular velocity goes up by 1. So omega of 0 is 0. Omega of 1 is 1 radian per second. Omega of 2 is 2 radians per second, and so on. So this is just the pattern that this is indicating to us. Now what we can do then is, let's do some comparisons. Let's say that we have this store, and we apply a force of 10 newtons, where our r is equal to 1 meter, and we get out an angular acceleration of 1 radian per second squared. Okay. Alternately, what we could do is we could keep most of the things the same here, except let's say that I double the force. So I'm going to keep the radius the same. We're still pushing at the same distance. I'm going to double f though, and what happens? We get an alpha of 2 radians per second squared. And this seems pretty consistent with what we had seen previously with force, mass, and acceleration. If we double the force, we get double the acceleration out. Now there are other things that we could do here. I'm not going to do them quite yet. Let's say that we have, instead, we apply the force further in. Actually, we will kind of do that now. So if I apply the force here instead, same amount of force, let's say, but only at half of the radius. So if I apply a 10 Newton force with r equal to 1/2 of a meter, we get out an acceleration of 0.5 or 1/2 radians per second squared. So we're getting out the whole torque idea here is what's happening. We find that when we double the force, we double the angular acceleration. When we have the radius, we have the angular acceleration. And so we can come up with kind of a general conclusion from this, that r times f, and we're not getting into the vectors too much just now because my forces here are all perpendicular to the radii, but we have r times f is going to be proportional to alpha. So if r doubles, we get a doubling of the alpha. If the force doubles, we get a doubling of the alpha. And remember, this r is referring not to the length of the door itself, but to the point at which we're applying that force. This isn't too surprising because I gave you previously a formula that involved this proportionality. The difficulty is, how do we figure out what that other proportionality is? Why is it this ratio that's happening? So I have 10 newtons of force, 1 meter, I get 1. 20 newtons, 1 meter, I get 2. 10 newtons, half a meter, I get 1/2. If I did 20 newtons and half a meter, I'd get 1 again. So it seems like there's this proportionality, and I'm getting 10 when I multiply these, right? With this one here, I get a 10, but I only get 1 out. With here, I get 20 as my product, and I only get 2 out. Here I get 5, and I only get 0.5 out. So it seems like what's happening is that there's a proportionality of 1/10. So I could do RF equals 1/10, actually not appropriate, equals 10 times alpha. So what I'm doing is, to solve for alpha, I need to divide by 10. The question is, why 10? What is going on that makes this 10? So that's what we're going to try to figure out next.